So in this particular R demonstration video, we're going to talk about ridge regression a little bit. Particularly, I wanted to focus a little bit on understanding the penalty function. So this will be a short video, but I wanted to take some time to understand the penalty function in ridge regression. But also, I also want to go into the idea of generating data or simulating data for our purposes. So the fact is that often when we are building new models in machine learning, in statistics and data science, we often have to test our models or test our new methodologies that we're coming up with on data that is well behaved and follows a certain pattern. By that I mean that recall that in our notes we often write that y is from normal distribution mean 5 variance 1. Now, if let's say I'm assuming something like this, if I'm assuming y is from a normal distribution with mean 5 and variance 1, then I need to see what happens to my method when the data are actually coming from this distribution. Because if my methodology does not work well, when data actually comes from this distribution, then it's likely not going to work well at all for real life data. So our baseline is that first I'm going to generate data. Okay. So first, often we want to generate data from the ideal data generating model. When we do that, then that means, let's say for the linear regression setup, our model is that y is equal to x beta plus epsilon. Okay, where in this particular case, beta may be in some, let's say, r to the power p, right? For example, now this could be, p can be equal to 2, p can be equal to 5, p can also be equal to 1. In this code, we're just going to look at 1, p equals 1. But it could be, you can change this code to be a bit more general as well. So now the question is, if this is the kind of model that we want, or this is the kind of sort of model we built, then we have to be able to understand what happens to our estimates from the model when the data are actually coming from this particular distribution or this particular modeling framework, which means I need to be able to so typically I'm assuming that epsilon follows some normal 0 sigma squared, for example. Okay. So to be able to generate x and y in such a way that x and y follow this actual distribution, I need to be able to generate epsilon from some normal 0 sigma squared, which means I need to set some sigma squared. Okay, so that's first task. Then I also need to set some beta, because beta doesn't come from some random process here. Beta is just some unknown fixed quantity that I want to find. So I need to sort of fix a beta star or a beta value that is the actual underlying truth from which the data is generated. And then my methodology is going to come and try to find this beta value. Okay, so this is really what we're doing here. And also, invariably I'm assuming there is some n or the number of samples that I want. So in this case, I'm going to assume that n equals 50. And so the first thing I do is, of course, set my seed so that your data and my data are similar. So I set my seed and I'm going to obtain 50 data points. So I do n equals 50. And then I set p equals 1, which means in this particular example, I only have one regression coefficient. Okay, and this part can be changed, so you can feel free to play around with this. Okay. And now, in order to actually generate my data, I set beta dot star, or the actual value of beta, to be 4. And then I just print it to understand that it is 4. Okay. Now, in some sense, now we forget what the beta dot star value is. In the sense, we will generate the data using this beta dot star, but I don't really need to know what the beta dot star value is after this point, because I want to make sure I never use my knowledge of beta dot star anywhere in our estimation, because the whole point is to estimate beta, the regression coefficient. Then I make my design matrix, which is basically the X matrix. And there are many ways to make this. And X is never typically assumed to be random, but one way to make this is just randomly obtain N cross P observations. My X matrix, X is N by P matrix, right? Now, because it's an N by P matrix, I know there are N times P elements. So I just generate some R norm N by P elements. I put them in a matrix such that they form N row and P columns. Okay, that's my X matrix. And then my Y is nothing but X beta plus epsilon. So I do X times beta dot star in this case. And epsilon is nothing but R norm or normal mean zero. And in this case, I do SD equals 1, which means I'm assuming sigma squared is 1. If I want, I can set a different value for sigma squared. I can set this to be 4, in which case sigma is 4, so sigma squared is 16. Okay. Oops. Okay, so this, when I do, I have then generated my data, right? So now after this point, one may forget that the data were artificial. Artificial meaning they were actually generated by a computer. They were not given to us from real world. Okay, but it's quite useful often to actually generate our own data and test our models based on generated data. And so this is why you have to understand, by using the model paradigm, what is the best sort of structure and way to generate my data. All right, that's one part of what I wanted to talk about. So for example, here I can look at, what Y is. If I look at header, or if I just look at Y should be 50 observations. And here it is. It's a column vector of length 50. And we see all kinds of different values on here. And if I look at X, I can do, head of X, for example. P is just 1. So X is N by P. So it's also 50 by 1. But now what I'm going to do is I'm going to make a plot of the two. So in this next part of the code, I'm going to make a plot of the objective function in ridge regression versus MLE regression. So for that, recall that ridge is negative log likelihood plus penalty, right? That's what the ridge objective function is. So that means first I need to have a function that calculates the negative log likelihood. Then I need to have a function that calculates the penalty. So the negative log likelihood is a function of the data that we've observed, Y and X, and it needs to be calculated for a grid of values of beta. Now this is why in this example I've set beta to be equal to 1, because if it's one dimensional, I can just draw a grid of values for beta and draw the corresponding objective function so that I can plot it in 1 dimension. Or sorry, 2 dimensions. Otherwise, if beta is 2-dimensional, I need a 3-dimensional function, a 3-dimensional plot to understand what the penalty or the objective function looks like. And when beta is 3-dimensional, I need a 4-dimensional plot, which I can't do. Okay. Now, the actual negative log likelihood, I know, comes down to Y minus X beta transpose Y minus X beta by 2. So that becomes simple. So that's my actual negative log likelihood function. And then there's also the penalty function. So the ridge penalty is for a given value of a lambda parameter. The penalty is just beta transpose beta by 2. Right? So this is basically just the ridge penalty over here then. So I can call that. And now it's simple. I'm going to create a grid of values for beta on the x-axis. I'm going to create a grid of 500 values. And these are going to be all my betas. These in this case will go from -2 to 10. Now at this point, you've seen me create grids of values before, so you should be comfortable with this. Okay. And I'm going to calculate the negative log likelihood. I'm going to also calculate the penalty term. Okay. And I'm going to finally also calculate the ridge term. Okay. When the ridge term, meaning ridge is nothing but negative log likelihood plus penalty. Okay. But I'm going to do it maybe for different values of lambda, but first I'm going to just fix lambda to be equal to 10. So once I do this, for each I in going from 1 to the grid of values is going to go and calculate the negative log likelihood for our data observed for this for the ith value of beta. Okay, and then it's going to go and calculate the ridge penalty for the ith value of beta. Then it's going to go and add up the negative log likelihood plus the penalty to get the ridge penalty term, the ridge objective function. I can do this. Great. And now it's simple. I have my the grid of values for beta. Using this, I'm going to plot the negative log likelihood. I'm going to plot only the penalty term, and then I'm going to plot the ridge term. And this is only the objective functions that I'm plotting. It'll take a second. There we go. Okay, so in black, we have the actual negative log likelihood term. So the minimizer over here, place where this is minimized, is actually nothing but the maximum likelihood estimator of beta. Now the penalty term is saying that as the beta value increases, it's going to give more and more and more penalty, right? Because it's beta squared or beta transpose beta by 2. So it's a quadratic penalty term. So as beta values increases, I get more and more penalty. And both of these curves together, when I add up, I get the blue curve. Okay. Right? And so this means that, when I have the ridge penalty included in my negative log likelihood, I get the blue penalty term. And because it's lifting too much in one direction, you basically get the minimizer happening a little earlier or a little before than the negative log likelihood expression, wherever the negative log likelihood is happening. Because I'm adding, I want to if, for example, the blue curve was not there, okay, or let me put it, maybe I can add one more point here. Yeah, I can, I think, add one more point here. But I can say, okay, points x is equal to 0, y is equal to 0, PCH equals 16, and color equals red. So you've seen me code live now. Let me remake this plot. Okay. So here are what the 3 dots are. The 3 dots are the individual minimizers for each of the 3 objective functions. I repeat now that the black objective function is the objective function that's coming from just the negative log likelihood, which means the black one corresponds to the MLE. The red one is the minimizer that's coming purely from the penalty term just being lambda times beta transpose beta. Okay. Now, this over here, the minimizer of this is 0 because the value when beta squared is 0 is at beta equals 0. Okay, so the minimizer is exactly 0. So now, when I've added both of these red and black curves together, I get the blue curve. And I'm not just adding them, I'm adding them by a factor of lambda, right? So when I'm adding these two terms together, their minimizer, wherever the minimizer of the new term is going to be somewhere between 0 and the black curve, depending on how steep this function is, right? So if I change lambda from 10 to 100, you are going to see the effect that this blue dot is going to shift more to the left. You see? Now when I made lambda equals 100, this is still my objective function. My negative log likelihood doesn't change. But the penalty term is now so strong, so much higher, that now the penalty term overpowers the actual objective function in the negative log likelihood, so that the ridge objective function is very close to the actual only the penalty term, which means that my actual solution, which is the ridge solution in blue, gets really close to the red solution, which is just the penalty term. Right? So there's basically a trade-off being the actual optimizer by only the penalty term, which is 0, the actual optimizer by only the negative log likelihood, which is the MLE. Right? So somewhere in between there's a tussle, and how much are we going to go towards 0 will depend on how big lambda is. So now if I make lambda to be 0.05 0, 1 or really tiny, then you'll see that the penalty term is really small, right? It's so small that we can't visibly actually see the negative log likelihood. So maybe instead of 0.01, we'll do 0.5. Now I can see the black is slightly different, and then the blue and black are slightly separate. Okay. So this is really what's going on in the penalty when you're penalizing the objective function. It's basically pushing the solution closer to zero, and the larger the value of lambda, the steeper that penalty, and the larger it's sort of pushing towards zero. So hopefully that sheds a little bit of light as to what's really going on behind this.